Greetings, YouTube. This is Dr. Schleif with another ACE Physics worked example, and you can see the question before us reads, explain what is meant by a scalar quantity and by a vector quantity. Scalar quantities have magnitude only, but vector quantities have magnitude and direction. Keep in mind these foundational ideas as we continue working through this question, which is clearly about some projectile motion. It reads, a ball leaves point P at the top of a cliff with a horizontal velocity of 15 meters per second as shown in figure 2.1. The height of the cliff is 25 meters. The ball hits the ground at point Q. Air resistance is negligible. Calculate the vertical velocity of the ball just before it makes impact with the ground at Q. So there's a component of velocity that's acting downward, and there's still 15 meters per second of horizontal velocity, right? Because that's constant, air resistance being negligible. So we're just calculating this vector here. I'm going to call this h, 25 meters. And so velocity equals initial velocity plus acceleration times time. This is just rewriting acceleration as the rate of change of velocity, right? So it's one of our equations of motion. So we could solve this for final velocity if we knew the time that it would take for the ball to hit the ground. Because we don't know the time, we could use this equation of motion and solve it without knowing the time, because we do know the displacement. It's very possible to solve for time. Remember our shortcut h equals 1/2 gt squared, which comes from the more general s equals ut plus 1/2 at squared. So because the initial velocity is 0 in the y direction, the displacement is this height, 25 meters, and we could readily solve for the time that it would take this ball to fall. I think that actually part 2 of this, they ask us to show that the time is 2.3 seconds or something like that. So the other thing that, students that sit for paper 2 in ACE Physics can do is, read ahead and say, okay, show that the time taken for the ball to fall to the ground is 2.3 seconds. Knowing that the time is 2.3, you could, substitute that into another equation where we do use time.
Ladies and gentlemen, at this point in time, the shelter in place is lifted. We are okay to resume normal activity. At this time, the shelter in place is lifted, and we are okay to resume normal activities.
And we've just been resuming our normal activities here in the physics lab. All right, so the final velocity v squared equals the initial velocity was 0. Remember, we're only considering the vertical direction. So the initial velocity in the vertical direction was 0. Twice the acceleration is going to be due to gravity, 9.81. I'm going to drop the units here just to tidy it up. And then the displacement was 25 meters. 50 times 9.81 is 490.5, and then we'll take the square root of that. So we end up getting, solving this for V, 22.15, you can just say 22 meters per second. So an object that falls 25 meters in Earth's gravity field is going to pick up 22 meters per second of velocity. So sort of solving it here. Let's see if this one would work too. So 0 plus 9.81, and then remember in the next question they say show that the time is 2.3 seconds. We're going to actually use this equation to show that, but let's just trust it for right now and see if that gives us the same 22 meters per second. 9.81 times 2.3. Sure enough, 22.5, so it might round to 23 if you're using, this value right here. Yes?
It was that it started at rest off the foot.
No, it just says that it has a horizontal velocity of 15 meters per second.
So are we assuming it started?
Well, it's not at rest if it's going 15 meters per second, but it's at rest in the vertical direction. You know, there's no, they don't tell us anything about it has an initial velocity in the vertical direction. So if they give you this kind of language, like a horizontal velocity of 15 meters per second, it can be assumed that the vertical, you know, velocity is 0. They don't show us any sort of, you know, vector there or anything like that. Show that the time taken for the ball to fall to the ground is 2.3 seconds. So we're going to use, as I mentioned a moment ago, h equals 1/2 gt squared. A very convenient way to relate the height of something, 25 meters in this case, to the gravity field, 9.81 meters per second squared, to the time it takes to fall. So just solving that for t, we would get see, 25 divided by 4.905. So t squared would be 5.09. That's just sort of, you know, dividing each side by 1/2 g, and then taking the square root of that. 2.257 is indeed about 2.3 seconds. Now, what if we use this 2.257 and we said v equals u plus at? Remember a moment ago when we plugged in 2.3, we got an answer that disagreed with this 22 that we got by using this equation, right? So when we use this equation, we get 22. What if we plugged in the more precise 2.257, and that's in my calculator, so times 9.81, and indeed you get an answer that agrees with this. That's a good sort of reminder to take care not to round your sort of intermediate calculations too soon, because then those rounding errors will sort of propagate through. So we get the same 22 meters per second when we use this or this equation. We just sort of plug in the more accurate time, 2.257 or something close to that, rather than rounding it to 2.3. If you substitute 2.3 seconds in here, you end up getting 23 as the velocity. So it's pretty close, but you know, a little bit off. Yes. Yeah, so you're saying 25 equals half of 9.81 is 4.905, and then just dividing both sides by that. So 25 over 4.905 is this, and that's equal to t squared. So I just distributing this 1/2 or taking 1/2 of 9.81 and then dividing both sides by that. All right, anybody following along at home, if you'd like to see any of the algebra worked out, just leave it down in the comments below. That's probably a good time to remind you to get on the Dr. Schleif notification squad. Don't forget to smash that like button. And be on the lookout for the Dr. Schleif merch. It's coming, you guys. It's coming. Calculate the magnitude of the displacement of the ball at point Q from point P. All right, so just the magnitude of the displacement. So it's a line that sort of looks like this. I forget which one was P and which one was Q, but it really matters, right? Kind of like that. Well, if we know that there's a component this way equal to 25 meters, right? That's the down component. We might be able to calculate the component this way by saying it should be equal to Vxt, right? The equation for range, because that's the sort of the horizontal displacement. So we'll use our range equation here to solve for this. And then we'll use Pythagoras' theorem to calculate the magnitude of the displacement. So it's like the straight line between where the ball landed and where it left the clip from there. Vx times the time airborne, I'm going to use 15 meters per second, the horizontal velocity that was given. And the time, I'm going to use that 2.257 value rather than the rounded 2.3. So I got that 2.2576, whatever number in my calculator, times 15. So that horizontally That ball would have landed 33.86 meters away from the edge of the cliff. So 33.86 is just the solution to the range. That number in my calculator squared plus 25 squared. So I've got this squared plus this squared in my calculator. It's like 1,771 for everybody following along at home. Taking the square root, we get a displacement of 42.092 meters, which rounds kind of nicely to 42. All right, make sure that you're answering the question that is asked. Make sure that you're diagramming it out correctly and you have a path to the solution in mind. Part 4 here reads, explain why the distance traveled by the ball is different from the magnitude of the displacement of the ball. This is pretty typical for things in the universe that travel, that the distance that they travel is going to be a little bit more than the displacement. So the actual trajectory of the ball was this parabola, right? It's like we kind of know that objects take that. But the displacement is just the net change in position. Remember, I reminded you way back when, keep the ideas of vectors and scalars in mind as we sort of continue to work through this, because this is exactly what it is. The distance traveled is a scalar. It's just how far did it actually travel along this path. And just by inspection, we can look at this and see that the straight line, path between P and Q is going to be less than the distance traveled. I think that brings us to the end of this worked example. But you might say to yourself, wait, that was question 2. Why didn't you do question 1? It's here, base units calculation. Well, boy, are you in luck. Bonus worked example, base units. Here we go. Underline all the base quantities from the following list. Take care for these questions that you know which are quantities and which are units, okay? An amp is a base unit of the quantity current. So current will underline, okay? It's a quantity. Amps are the units we measure current in, okay? Charge is not a base quantity, but I argue that it should be. We should replace this one with charge, but maybe someday. Right now, current is the base quantity. Is mass a base quantity? Yes, and we measure it in the base unit, kilogram. Second is not a quantity, right? It's a unit. It's the unit of time. Time is the quantity. Temperature is indeed a base quantity, right? It's measured in the base unit. Leave it down in the comments below. All right, you got it, Kelvin. Well done. Now, weight is a force, and force is not a base quantity. Force is not a base quantity, and so neither is weight. The potential energy E sub P stored in a stretched wire is given by this equation here, where C is a constant, sigma is the strain, V is the volume of the wire, and we are to determine the SI base units of C. All right, so potential energy is measured in joules. That's a derived unit. If we were to remember what the base units are for energy, we could just say, oh yeah, I got it memorized. Kilogram meters squared per second squared. And if you don't have that memorized, then you might say, well, what equations could I use to sort of, arrive at that there? Work equals force times displacement. And so a joule of work is equal to a Newton meter. Okay, a Newton of force times a meter of displacement. And you may recall that a Newton is a kilogram meter per second squared, right? And that comes from F equals ma. So the Newton being this, multiplied by another meter out here, gives us these units for energy, the base units for energy. On the right side of this equation, the units of this fraction 1/2 are nothing. It's just a number. So it doesn't have any units, so we won't really care about it for this. C is the thing we're trying to figure out, so we'll kind of just leave that as a C, but I like to kind of put a box there. Like C is what goes in that box. That's going to make everything work out here. Sigma is the strain, and it's squared here. What is strain? Let's see, stress. So strain is just the extension divided by the original length. Okay, it itself is dimensionless, right? Because it's a ratio of two lengths, right? So it's like if we stretch out a wire, x, the extension, like how much longer does it become over its original length? It's a ratio of those two things, and so it itself is dimensionless, and something that's dimensionless squared is still dimensionless. So there's no units coming from that sigma there either. So that's kind of nice. And all we've got is the volume over here. Well, volume is just going to be length times width times height, so meters cubed. And so, well, what are we missing on the right side in order to get it to look like the left side of the equation? Well, we'll need a kilogram in there. We'll need to cancel out one of these meters, and we'll need to get some seconds squared down there in the denominator. And now if we were to multiply kilogram per meter per second squared by a meter cubed, we'd find that the left and the right side agree, right? So the base units of energy, kilogram meter squared per second squared, equals kilogram. And again, one of these meters is going to cancel, or this meter is going to cancel one of those. And so we just get meters squared per second squared. That's a homogeneous equation, right? It's the same on both sides. And so the answer to this, the SI base units of C, are everything we had to put in this box for C, right? So it's going to be a kilogram per meter per second squared. And this has been another worked example or two with Dr. Schleich, still living the physics life. We'll see you guys next time.